Awesome. All right. Well, thanks so much, Boxin, for being here, and thanks everyone for coming to the Flow seminar today. So just as a reminder, if you're new to the seminar, this is a seminar that takes place roughly once a week on Wednesdays, and it covers topics all in the space of federated learning. And it's something that started in the pandemic, and we've continued doing it over the last couple of years, just because it's been a nice way to stay up to date with research in the area of federated learning. Today, we're really fortunate to have Boxin Wang with us giving a talk. So he's a PhD student at UIUC, working jointly with Professor Bo Lee, and works broadly in the area of trustworthy machine learning and natural language processing. And today we'll be talking about large language models in conjunction with cross-device federated learning. So definitely an area, I think, of a lot of interest, especially recently. So we're really excited to hear more from him today and learn about some of the insights from some of his recent work. So Boxin, I'll pass things over to you. And if anyone has a question during the talk, please feel free to put those questions in the chat window. Or if you use the raise hand feature, I can help to unmute you and you can ask a question. And Boxin, I'll try to just alert you in case there's a question hanging out in the chat window or something like that. All right, thanks. Go ahead and I'll pass things over to you.
Cool. Yeah, thanks so much for the introduction. So hello everyone. First of all, I would like to express my sincere appreciation to everyone for joining the seminar. It's really a great honor to present here. So also a big thanks to Professor Smith for giving me the opportunity. A brief introduction about myself. I'm Boxin Wang, and a fourth-year PhD candidate at UIUC, and also meantime full-time research scientist at NVIDIA. I'm very fortunate to be advised by Professor Bo Lee. The topic of my presentation today is on how to leverage large language models to help private cross-device federated learning, which was done during my internship at Google last summer. So I would also want to like to thank my awesome collaborators from Stanford, Google Research, and Google DeepMind for their great help. And I think today we also have Zheng and Yibo come here. So among which Zheng is my internship mentor and is the best mentor I've met during my PhD journey. And Yibo is my my friend and from Stanford. He helps a lot on the theoretical part of this work. So feel free to reach out if you have any interest or questions. And so the first part of this talk is around 40 minutes of introduction of my work, and I will leave the remaining time to Q&A. All right, so maybe let's get started. So in recent years, the landscape of AI has actually been significantly altered by the advances in pre-trained large-scale language models. And scaling up models with more data and parameters has significantly improved the performance and achieved great success in a variety of applications, from like natural language understanding to multimodal representation learning. And these large language models, such as like NVIDIA's Magnetron 2 NLG, to the recent Lambda from Google and the GPT-4 from OpenAI, has drawn a lot of attention from the community. And they also yield a lot of game-changing applications, such as code completion tools, as well as like dialogue assistant. On the other hand, differential privacy provides a rigorous guarantee to quantify the privacy bound during training, and DPS-GD algorithm adds noise during the gradient updates and provides an easy replacement of SGD when we do model updates, but with like strong privacy guarantee. So this so recently people are focused more on developing differential private language models with like strong privacy guarantee, and like from a recent literature, the community shows that large language models actually can be strong differential private learners. And specifically, when we add the performance gap between non-private training and differential private training, they observe like smaller and smaller gap when we scale up the model parameters. And this is largely due to the success of like large scale pre-training, because during the public pre-training time, they can learn a lot of things that can be helpful for downstream private application. Well, in our work, we mostly want to focus on this regime that is for models of like for on-device models like on-device LSTM or on-device transformers with like around less than 10 million of parameters. And so in previous application, we see there's a huge like non-private and private training gap. And this motivates us though to raise the question that can we leverage large language models to close this gap for differential private or federated learning? And the answer to this question in our work is yes. And specifically, we try to answer this question from the following three perspectives. The first perspective is the inspirations from large language models. So what's the takeaways or lessons we have learned from large language models, and can we transfer those knowledge to those like on-device models when we do the training? And another thing is another perspective is distillation from public language models, because now that we have already like very well-trained like public large language models, can we just distill a large language model and use that for on-device models and see how it works? And lastly is about our novel contribution on distribution matching algorithm, where we further improve the sample efficiency to sample like public records that is close to the private distribution, and they yield like similar performance as like public like distillation while using significantly less trained data. So I'll give more details in the later slides. So let's first get started on the first perspective, that is what's the inspiration from large from our when we pre-train the large language models. So remember, like for large language models, they have like very advanced tokenizers. So I will first start with the tokenizer part. So for the private in our differential private federated learning setting, from the literature, we see that most existing work use like private tokenizers that is constructed from a private corpus, specifically unigram vocabulary. And this vocabulary comes from the most frequent words in the private data set, and it consists of around like 10K or more words. In comparison, we also noticed that the public model leverage of like a very advanced tokenizer that is a public tokenizer. For example, take the example as Lambda, it uses sentence piece tokenizer from public corpus, and the vocabulary can consist of around 32K tokens. And in the figure below, I show the differences between a word piece based tokenizer versus word based models, where you can see like sentence piece tokenizers will like further split each word into like smaller units called tokens, and one word can consist of multiple tokens. And in our study, we first noticed that if we just replace the existing like private tokenizers to public tokenizers, it not only can save us like prevent us from like the potential privacy leakage issue, because the vocabulary is from the most frequent words in the private dataset, which may have some potential privacy issues, but also can actually give us better private learning accuracy. So here's our setting. We first at this point, we do not do any like public pre-training. We just do private federated learning for like on-device models. On the private, here we use Stack Overflow dataset as a private dataset, using the DPF-DRL algorithm. For our on-device models, I use one layer LSTM with 3 different choices of different tokenizers. So the first is the unigram tokenizer from the private corpus, and the vocab size is 10K. And the second is the unigram tokenizer from the private corpus, but the vocab is increased to 32K. And the third is the sentence piece tokenizer from large language models, which also has the vocab size equal to 32K. And I evaluate the next word prediction accuracy after like private federated learning, and I concentrated on 2 differential private settings with delta both equal to 1e minus 6. The first is we have smaller number of noise, that is set a noise multiplier equal to 1.13, which yields the epsilon equal to 18.71. While if we use like larger noise, we can have a like tighter epsilon bound equal to 1.77. And to make the word-based model and token-based model comparable, during evaluation, I convert next word prediction accuracy to next token prediction accuracy for unigram tokenizer. And this is done by consider all tokens within a word as correct if the predicted word is correct. And here's our results. So from both tables, from both figures, we can see that when we first use unigram tokenizer with vocab equal to 10K, the accuracy is around 21.19 for epsilon equal to 18.71. But if we use a larger like unigram tokenizer, the next word prediction accuracy will actually drop. And similarly, if we convert it to the next token prediction accuracy. However, even with the same vocabulary size, when we just replace the tokenizer from the unigram tokenizer to the more advanced sentence piece tokenizer, the next token prediction accuracy just increases like a lot. So this suggests that just using a more advanced technique in terms of the embedding or the vocabulary selection, this can give us some already some benefits, and moreover it can mitigate the potential like out of vocabulary issues. So yeah, this is the first takeaway we have from the large language models. And the second, of course, is the success of large language models is due to the large scale pre-training. And so we also do this pre-training for like on-device models, and we actually follow the exact same like similar way that we run public pre-training on the whole public data set. Specifically here we use C4 dataset, and then we run the private federated learning on the private dataset, which is the Stack Overflow dataset, by after loading the pre-trained checkpoint. And we noticed that actually pre-training is very, very helpful for differential private settings for both like smaller noise or larger noise. And specifically, we can see the gap is, we can see at least the 5% accuracy improvement by just adding the pre-training before private training. But the issue is that conducting this like large scale public pre-training on the whole C4 dataset can take us like almost a week to finish, even for on-device models. So this is, as you can see, this is very time cost and not very efficient. So this motivates us to delve into the second dimension, that whether we can just distill from existing like well pre-trained public large language models. So yeah, and to do that, we actually construct the distillation corpus. So given the pre-training corpus, we try to extract the large language model's output, which is a top K lodges, and dump it as a silver label dataset. And during pre-training, we just like kind of follow the existing like distillation literature that leverages both gold label pre-training dataset as well as silver label distillation dataset. And so you can see our pre-training loss now consists of two parts. The first is the standard like pre-training loss to predict next words. And the second part is the knowledge distillation loss, which beta is the a coefficient to balance these ways. And and we want to let the student model or on-device models output to like learn or mimic the distribution of the large models or the teacher models logic distribution. And you can see such design is student model agnostic. So we can actually, it's flexible for us to use this pre-training loss for whatever on-device models such as LSTM or transformers as student models.
Can I ask a really quick question? Does this,
Yeah.
that previous procedure requires having the pre-training data as well, is that right? Okay.
Yes, exactly. And actually, this is what the message we will show here. That is, during distillation, we actually just need 1% of C4 corpus, and the performance will outperform using 100% of C4 corpus for public pre-training, but without language model distillation. So the settings like here we're doing like public pre-training on the randomly sampled 1% public data set, which is safer data set again. And but this time our 1% public data set has both gold labels from ground truth or the corpus, and the silver labels, which is the largest from the large language models. And then we, after do this like LM distillation on public corpus, we do the second round, like the private federated learning for on-device models on the private dataset, which is Stack Overflow dataset again. And we show that distillation is further helpful and with like even less data. And the improvement is further like significantly in the low epsilon regime, where we can see like when we have small epsilon, there can be more than 2% of improvement. And we also done some like ablation studies, which include like how we do distillation. For example, we noticed that when we dump the large language models logics, we will save the like top K logics for the knowledge distillation. And now we try select different top K teacher logics, and test on the and then run the private federated learning and see what's the downstream accuracy. And so the following figure is that we load different distill checkpoint at this different pre-training steps, and this pre-training like uses different top K logics, and we can see that using a little bit larger top K, like top K equal to 10, can always give us like better performance when we do the distillation. And it's true for both like small epsilon and large epsilon. And we also noticed that if we further do the distillation, so previously we just do like 1% of C4 dataset for distillation, but in this figure we show that if we distill the large language models for kind of more epochs, does not actually improve significantly. Specifically, I'm again loading the distillation checkpoint at more like training steps, like pre-training steps, and then I run the DPFL. And the public pre-training can cover like from 1% to 26% of C4 dataset, and we show that. And following the takeaway of the last slide, I will use the top 10 logics as the teacher logics CT, and we show that when we continue to do the like distillation, the accuracy actually remains like barely improves. So probably using just 1 or 2% of C4 dataset with distillation can already give us like quite good performance. Yeah, so and the last dimension I would like to emphasize today is on the distribution matching algorithm. And the main motivation is that in the previous section, we're just actually using 1% of randomly sampled pre-training corpus with LLM distillation, and this is pretty good. And our question is, can we further improve the training efficiency by carefully sampling pre-training corpus and reduce the training cost then? And this motivates us the following distribution matching algorithm. And the main intuition is that we want to select public data close to private distribution. And how do we sample those public data? My first intuition or hypothesis is that we want to sample records with both high probability on the private data distribution, so that is of course close to the private data domain, and this can probably be estimated by the privately fine-tuned on-device language models. And on the other hand, we probably want to sample records with high probability on the public data distribution, because those data may be of like high data quality or easy to learn samples, and which can help models to converge. And this can be estimated by public pre-trained large language models. And to verify our hypothesis, I first conducted an empirical experiment on our previous data set. So we can see the figure below. The blue regime denotes the private data set distribution, and this is characterized by the public LM perplexity and private language models perplexity. And we can see actually the private data are almost concentrated on the regime with low public and private language model perplexity, or in the other words, high public or private language model probability. And on the other hand, we can see the public data set, which is the orange regime. It is more diverse and harder. So this motivates us to sample, to get samples with low public or private language model perplexity from this orange regime, the public data set that overlaps with this point, this private data distribution, which kind of confirms the intuition of our approach. But before we conducting more experiments, we also try to think about it in a theoretical way. So remember, so first I'll introduce a little bit notations. So define our text data domain as X, and we denote LPUB, which is log density function of our public data distribution. And so you can see the LPubX is log P PubX, where P PubX is the public data density estimated by large language models. And we also want to denote the LPriv as the log density function of the true private data distribution. And the reason I want to emphasize true is because I will have another notation that is LPriv hat as the log density function of inaccurate private data distribution. The reason I'm saying is inaccurate because it is estimated by the inaccurate private data density estimated by the on-device language models. And the reason is inaccurate is because first is the on-device models have limited capacity, and the second is we add a lot of differential private noise during pre-training. So you can see this estimation can be not that accurate. So so essentially our distribution matching algorithm tries to find a good estimator for the private data distribution LPriv. And before we go into details, we also want to mention that this LPriv hat is can be understood as a random variable, where the randomness can come from like the private data set is sampled from the private data distribution, and the randomness, and there's also randomness in the algorithm training, like when we do the differential private training. With that being said, we can do some more definitions, like for example, we can define the better or the closeness of between different distributions. And specifically, we can, well, first we can have a inner product in the function space of H, which maps the text domain to a real number. And then we can define the norm in this function space H is defined by this inner product. And then we can characterize how close is our estimation is. So specifically, we can see why the previous two like estimation is not accurate. First, if we just use the public data to do the estimation for the private data distribution, we can see there is a public-private domain distance, and we carefully notice here, denote it in here. And if we just use the private data to estimate the private distribution, there will be we notice that this difference is here. Remember this this definition because they're important as we show next. The quality of a private log density estimator could depend on these two like quantity, this public-private domain shift and the private domain randomness. So specifically, let's like characterize the error of a arbitrary function f hat to be this, and then of course by the definition the public distribution arrow is like d pub priv square, and the private hat L private hat the arrow of this is like sigma priv square. And then if we record our previous intuition or hypothesis is that we want the samples to have both like high probability in terms of public records and private records. So we kind of have mathematically we kind of have a private estimator like H hat here, which we try to sample records that has both L pub and L priv hat. So and then we can actually depict the L hat, the error of L hat in terms of these two quantities. And what does it imply? So it implies that first so the H hat can be, so the first quantity implies that the H hat can be better than either L pub or L priv hat for any settings. And moreover, we can expect H hat to be better than both L pub and L priv hats if there is a domain shift between the public private domain and which is the denominator, and our estimated private log density L priv hat is noisy in an extent comparable to the domain shift. So our H hat will be better than both L pub and L hat priv. So and also note that this H hat, if the coefficient here, the like 1 divided by 2 is like kind of our like empirical settings, and this can be, there probably be more like optimal beta here, and we discuss it in our appendix in our paper, and feel free to take a further look at that. All right, so previously we kind of go through both empirical intuition and theoretical intuition on our distribution matching algorithm. And now how do we actually do our distribution matching algorithm, and how do we incorporate in our model training? So essentially, our algorithm consists of the following 5 stages, and notice that our distribution matching algorithm actually features for 2-stage differentially private federated learning approach. So in the first stage, we train our undevised language models for rounds t prime, and this t prime is less than t. The reason we want to do first stage private FL is because we want to first get a okay undevised language models for the private distribution estimation, and then we just use the and then for each samples in the public records, we just do probability evaluation, and we will calculate the log probability of priv and ppriv and ppub, and store it. And in the distribution matching part, we will sort the our public data set based on these two scores, and sample a subset of the prime with those top values, such that this d prime is q times like d, where q is the sampling rate we want to have, and then we use this sample records to conduct kind of mid training. So it's not now we are not like doing pre-training where insert this public training in the middle of two like DPFL stages, and then we train these undevised language models with the distillation loss we just mentioned, and after we finish the pre-training or the mid-training, we do another round of or do another stage of private FL, use the remaining like privacy budgets, and then we'll return our undevised language models with DP guarantee. And actually our takeaway in our experiments, it shows that using just the 0.08% of C4 public LM or the Q, so you can see the Q here is 0.08, with distribution matching can actually outperform 1% of C4 public LM distillation, but without distribution matching, but just purely random sampling. And recap, in reality or in practice, our experiments, like we first do 800 rounds of private federated learning on the private dataset, and then we use the DP tuned undevised language model to perform distribution matching, where we'll use both undevised models and large language models to get the probability and select those 0.08% of C4 dataset, and with the lowest perplexity, and then we'll distill a public LM to these undevised language models using the sampled public data, and then we'll use the remaining private budget to complete the other half rounds of DPFL for the last 800 rounds. And from the figure below, we can see that well, first of all, the performance is actually similar or even outperformed a little bit than the 1% of public LM with distillation. But moreover, we are just using 0.08% of C4 dataset. This means that we actually reduces our, like, remember at the beginning of my talk, I mentioned that during the whole dataset pre-training, it can take us almost a week to do the public pre-training. And now with just 0.08% of C4 dataset, we can reduce the pre-training time from a week to just a few hours of GPU hours. So this is a huge training efficiency improvement. So as a summary, we can actually depict our conclusions in terms of these two axes. The x-axis is the accuracy, while the y-axis is the number of training samples we use. And we start from vanilla LM, and then we use a lot of C4 dataset, and we show that by doing this public pre-training, it can give us significant performance improvement. And then we try to reduce the number of training samples by using distillation from large language models. And this not only gives us better performance, in terms of accuracy, it also gives us better data efficiency by just using 1% of C4 dataset. And lastly, we introduced distribution matching algorithm which further improves the downstream accuracy and the sampling as efficiency, where we just using 0.08% of C4 data set, and we can achieve like quite good performance, as well as like with minimal number of training samples. All right, that's pretty much today's talk. So let me know if you have any questions. We also include more interesting application studies in the in our main paper and appendix. So feel free to take a look. Yeah, thank you.
Awesome. Thanks so much. Yeah, so please feel free to put your questions in the chat window or raise your hand. I have one quick question just to get things started, and then it looks like there's some things in the chat window. I wanted to double check two things really quickly. So one is, do you think that the results are in any way specific to using DP-FTRL? It seems like you could replace that with other approaches, like just standard DP-SGD. It looks so like in the algorithm that you put up there, it looks like you were using DP-FTRL in all of the experiments. Is that right?
Right. Yeah, so for all of experiments that have we using DP-FTRL, and the reason is because this is actually, as far as I know, the most kind of practical algorithm, because it like eliminates the sampling, because it gives a rigorous it gives a rigorous analysis for the sampling part, because the previous the standard DP-SGD requires we're uniformly sampling from a private corpus, but now we can just go over the whole private records and yield our privacy bound. So this is why we use DP-FTRL, right?
Okay. But do you expect the results to be to change at all? It seems like they would be agnostic to the method that you're using there.
Right, I think so, because especially it's just I think it's just the privacy like a counter a little bit, it changes a little bit, so it just does not impact our noise multiplier or anything else. So I think our conclusion should work for other like DPFL algorithms. Yeah.
I guess one quick related question I had related to that is whether it seems like the results that you had held sort of regardless of the value of epsilon. What do you anticipate to happen there? Like, do you expect there to be some value of epsilon such that pre-training isn't that useful, or maybe becomes very useful like small? I'm curious what you think the trend would be there.
Yeah, thanks for the insightful question. Actually, we have a ablation study, but I didn't put it here. So where we show that our distribution matching algorithm may not be that helpful when we use smaller number of noise. So remember, like in our privacy analysis, in our theoretical analysis, there are two types of arrows. One is the public-private domain shift, and one is the randomness we added. So if we use like large epsilon or smaller noise, you can see this arrow is kind of very minimal. So now it's kind of no longer comparable to the public domain shift. So this means that if we just use the private model alone for the distribution matching algorithm, it can also give us like pretty much good accuracy. So without a large language models for the like public domain shift, it can still give us like good performance. So this is one way to one applications or interesting observation we found during our experiments. Yeah. Other than that, we always see that our algorithm kind of works great for for both high epsilon and low epsilon, and usually like larger improvement margin for low epsilon part or larger noise part. Yeah,
got it. Okay, interesting. There's a question in the chat window. I don't know if you can read that on your end, but I'll just read it out loud. So there's a question about the tokenization results. So the question is, when you obtain a tokenizer using private data, are you training that with DP-SGD? Are the pre-trained model weights also fine-tuned in those experiments?
So first of all, the private data is the private tokenizer is obtained in this way. So we just use the kind of most frequent words in a private data set. And so it does actually not involve any training in this tokenizer. And this also follows it's just to follow the existing literature in like the next token prediction experiment set. And are the pre-trained model weights. So we do not so when we do the public pre-training for our on-device models, we will then load this pre-trained model checkpoints or model weights, and then fine-tune or actually doing the differential private FL on this on-device models weights, and so that it's more adapted to the private domain, and we report the next token accuracy after DPFL. Yeah. Does that answer your question?
I think I might have unmuted you, Kevin. Okay, you got it. Okay.
Okay,
Awesome.
cool. Thank you.
Okay, great. Yeah, I have one last question. And yeah, feel free to put more questions in the chat window if anyone else has follow-ups as well. I just wanted to check. So I'm imagining, because you're thinking about cross-device federated learning, you maybe have a sort of like trusted central server assumption. I'm curious about whether the distribution matching approach could potentially reveal sensitive information itself, or maybe it'd be worth walking through that again. Like if you, for example, if you didn't have trust in the server, I mean, it seems like a difficult problem, but could the matching method itself potentially reveal any sensitive information from the private data? Like what is being sent from the client to the server?
Yeah, it's a very nice question. So first of all, I would say the public training is conducted on server side alone. And also, remember the reason we want to do this two-stage DPFL is that we want to make sure our on-device models that is trained with DPFL has like privacy guarantee. So this means that the data sampled by this DPFL has also privacy guarantee. Because the model is sanitized by with like the epsilon delta bound, and
so you're just using the private model for those calculations, is that right? So in the first stage you train the private, or so what I didn't understand is when is the model being accessed, and is the model like private at the time it's being accessed?
Yeah, sorry for the confusion. I should make the algorithm part more clear. So after the first stage of DPFL, we get these on-device models, and which will actually give us like this log p priv x, and to compute the average log probability given this private fine-tuned on-device models. And so we will just use this private model to calculate this private log probability, and use the public model to calculate its public log probability. And during distribution matching, we'll calculate this score, which is we add these two probability together, and we will sort the corpus D with the top these values such that we will use them for the further like public training.
Got it. Okay, and this is all happening on the public pre-training corpus, is that right?
Exactly.
Got it. Okay, cool. All right, interesting. Any further questions from folks? All right, awesome. Well, thanks so mumuch again. Yeah, super interesting talk, and I really appreciate you taking the time. So thanks so much.
Yeah, thanks so much for the invitation.